Good morning, one and all. I heartily welcome all the participants in a one-day webinar on principal component analysis, theory, application, and interpretation using AgriAnalyze. Myself, Darshan Kothiya from AgriAnalyze. Today we cover principal component analysis. In that, first, what is univariate, what is bivariate, and what is multivariate data. Then, challenges associated with multivariate data, then PCA, then selecting principal component analysis components, then PC score and PC loading. After covering this theory or how to construct PCA analysis and how to select the number of principal component, we have to see that how to analyze PCA analysis of your data with AgriAnalyze. So last output of PCA in AgriAnalyze was given in this PPT. Okay. So start with univariate, bivariate, and multivariate data. Because PCA analysis is a multivariate data analysis technique. So univariate, like if we study with only one variable, like it is yield. Okay. So based on this only one character, we divide our all the genotypes in three categories, like higher yielder genotype, then moderate yielder, then lower yielder genotype. Okay, so here we cover only single variable at a time. So that's why it is a univariate. This is a univariate data. If we cover only single variable at a time, then it is a univariate data. So let's see data involving the measurement of only one variable on each observational unit. Each observational unit here is genotype. So here we have a genotype is our observational unit and our character is yield. So based on this, we divide our all the genotype into three categories: higher yielder, moderate yielder, and lower yielder. Then bivariate data. So bivariate data, if we have a two variable like yield and another is days to maturity. Days to maturity. Okay. So we divide our genotype in, let's see, higher yielder, and early mature. Okay. Second category is higher yielder but late mature. Okay. Then third category is lower yielder but early mature. Then fourth category is lower yielder but late mature. So here we divide our all the genotypes into four categories based on two variables. First one is the yield and second one is the days to maturity. So here we study with two variables. Here we study with two variables or two traits. So this is the bivariate. This is bivariate. In univariate, we study with only single variable, while in bivariate, we study with two variables. So bivariate data involving the measurement of two variables on each observational unit, generally used to study the relationship between them. Okay. Like in correlation, we study with yield and plant height. Okay. Like in other example, height of the student and weight of the student. So if height is increased, also weight was also increased. This is the positive correlation between them. So that type of relation which was shown in bivariate data. Okay, like height of the student is decreased, then weight of the student is also decreased. Okay, so this is the positive correlation. It means both the variables, direction of both the variables in a single direction. So this is positive, and another is if like yield is increased, then plant height is decreased. So this is the negative correlation. That type of relation which was shown in bivariate data. So bivariate data is used two variable at a time. So that's why it is a bivariate data. Then multivariate data. So in our agriculture example, like in breeding program, we study with more than two or three variable like yield, plant height, biological yield, then days to maturity, then days to 50% flowering, then a number of branches, then number of pods, number of seeds per pod, test weight. So here we have a more than 2 variable at a time, and we classify them genotype in the basis of more than 2 variable. So it is the multivariate data. So if we study with 3 or more than 3, if we study with more than 3 or 3 or more than 3, so this is the example of multivariate data. Multivariate data. So data involving the measurement of 3 or more variables simultaneously on each observational unit, allowing the study of relationship and patterns among multiple variables. Like, so let's see, if we consider only single variable, then it is univariate. If we study with 2 variables, then it is a bivariate. If we study with more than 3 or more than 3, then it is a multivariate data. So in our agricultural, most of the example which was shown in multivariate data. So this is the most appropriate and most useful data for in our agriculture. In short, univariate has a 1 variable, bivariate has a 2 variable, and multivariate has a 3 or more than 3 variable. Okay. Now, if we study with multivariate data, then we have some challenges which is associated with multivariate data. So first we see that when the number of variable increasing, the data set become high dimensional, making it difficult to visualize and interpret the overall pattern of observation. How? Sorry. Like if we have only 2 variable, like this is the plant height and this is the yield. This is the plant height and this is the biological yield. It means biomass of the plant. So here we have a data like this. It means if plant height is increased, then biological yield was also increased. So this way we can see this is the pattern of our data. Okay. So if we have a 2 variable, then it is easy to visualize our data. But if we have a 3 variable, like 3-dimensional data, then data is look like this. So it may be difficult to interpret or difficult to visualize our data, So this is the most challenging to visualize our multivariate data. It is very difficult to also interpret our data. So this is the most challenge which was associated with multivariate data. Then, moreover, many variables are often correlated with each other, resulting in overlapping or redundant information. So we know that in multivariate regression analysis, first assumption is that no multicollinearity. It means if we in multiple regression, if we have a x1, x2, x3, and x4. So here we have a pair of x1, x2, x1, x3, x1, x4, and correlation between them, it should be non-significant. Okay, it should be non-significant. It means correlation between these 2 variable x1, x2, x3, x1, x3, x4, x4, it is a non-significant. It must. But in multivariate data, it may be correlation is significantly found. Then our results found standard error in multivariate regression, standard errors found increasing, or our results may be misinterpreted. Misinterpret result. So if multicollinearity is present in our data, then in multivariate regression analysis, results found highly error, or results may be misinterpreted, or prediction is also difficult if multivariate collinearity is present in our data. So first we have to remove this multicollinearity in our data, then we have to perform multiple regression analysis. So how we have to remove this multicollinearity? So here we use PCA technique. PCA technique. Okay. In if multicollinearity is present, then we use PCA. How we see in next slide is, therefore, analyzing all variables simultaneously may become complicated, particularly when the objective is to identify the major source of variation or compare genotype based on several traits. I explained in previous slide, like if we have to classify our genotype based on yield, so it is very easy. If we classify our genotype based on yield and days to maturity, then it is easy. But if we classify our genotype based on 3 or more than 3 variables, so it may be very difficult to classify them. So this is the most challenges which was associated with multivariate data. So here we have required one test, statistical test, which was used for multivariate data. So this is PCA technique, which is also known as dimensional reduction technique. Dimensional reduction technique. How? So if we have a 3D data, it means if we have a 3 variable. So PCA is transformed in 2D by using PC1 and PC2. Okay. So if we have a data look like this, X, Y, Z, so it transforms in only 2 axes, PC1 and PC2. So principal component analysis addresses this problem by transforming the original correlated variable. So here all the variables in multivariate data is correlated with each other. So this PCA technique transforms these correlated variables into a new set of uncorrelated variables. It is called principal components. So here, like if we have a x1, x2, x3, x4. So first, PCA make 4 principal components: PC1, PC2, PC3, PC4. These variables are correlated with each other. It means original variables are correlated with each other. But PC1, PC2, PC3, and PC4 are orthogonal to each other. Orthogonal means it is a uncorrelated. It is a uncorrelated with each other. That's why it is a orthogonal transformation. This is principal component also known as orthogonal transformation. Orthogonal means uncorrelated with each other. Okay. So let's see what is PCA and who give these techniques. So it is a simple non-parametric method. Why non-parametric? Because principal component is now not required any assumptions. This technique does not require any assumptions like normality or any assumptions which was required for other techniques. So here principal component analysis, there is no requirement of any assumptions like normality of data or other. Then it is a simple non-parametric method of extracting relevant information from complex dataset. Why complex dataset? Because our data are correlated with each other. If correlation is there, so this is the complex dataset. Or we have a high dimensional data. High dimensional because we have a multivariate data. So PCA is a statistical procedure that uses orthogonal transformation. Why orthogonal transformation? I say that because it transforms the original correlated variable into uncorrelated variable to convert a set of observations of a possibly correlated variables into a set of values of linearly uncorrelated variables. Why it is linearly? I explain in next slides. So that's why it is called principal components which are orthogonal to each other or which are uncorrelated with each other. This technique was first introduced by Carl Pearson in 1901. It was independently developed and named by Harold Hotelling in 1930. Hotelling also gives another techniques like Hotelling t-square, which was extension of a t-test. It was also extension of t-test. This t-test is used for univariate or bivariate, while Hotelling t-square is used for multivariate data. Then PCA was first applying ecology of woodland under the name of vector analysis. So first, principal component analysis is a part of vector analysis, but later it was a independent test. It is called principal component analysis. First, it says that vector principal component analysis. PCA is method for identifying the pattern in data and representing the data in a way that highlights similarity and differences among the observation. Why similarity and differences? Because it's based on variance covariance matrix. Because it based on variance covariance matrix. Like variance covariance matrix is look like this. Like if we have a two variable x1 and x2. Okay. Okay. Variance covariance matrix is look like this. Like S is equal to, like if we have a two variable x1 and x2. So here diagonal element of this matrix shows the variance of independent variable. Like x1, for x1 variance of x1, and this diagonal element shows the variance of x2. Okay. Diagonal element, it means if we have a 3 by 3 matrix, 3 by 3 matrix, then this, and this. So this element is called diagonal element. Okay. And this matrix, if diagonal elements is look like 1, 1 and 1, so it calls identity matrix. This is used in our principal component analysis. That's why I explained this identity matrix. If diagonal element is unity, then this is the identity matrix, and this is diagonal element of matrix. Okay, this is upper diagonal, this is upper diagonal elements, and this is the lower diagonal elements. And in identity matrix, upper diagonal and lower diagonal matrix is 0, and diagonal matrix diagonal element is equal to 1. So this is why, that's why this is called identity matrix. So here in variance covariance matrix, diagonal element is shows variance of independent variable or our given variable x. This is the variance for x1. This is the variance for x2. And this element of matrix is shows the covariance between x1 and x2. x1 and x2. Covariance means it is the simultaneously variation was explained by x1 variable and x2 variable. And this covariance which was used in correlation. If we want to find the correlation between x1 and x2, so this is the equation for correlation. So it is the covariance of x1, x2 divided by standard deviation of x1 and standard deviation of x2. Okay, so this is the formula for correlation, and this value shows the covariance between x1 and x2. This value shows the directional relationship between x1 and x2. If covariance found negative, it means x1 and x2 are negatively correlated with each other. It means if plant height was increased, then yield was decreased. So covariance between plant height and yield, it is negative. It is negative. If plant height was increased, then biological yield was also increased. Then covariance between plant height and biological yield is positive. So this sign, negative sign and positive sign of a covariance between two variables shows the directional relationship between two variables. Okay. Up to this, anyone who have a question? If anyone has a question, please ask me. Okay. Patterns can be difficult to identify in high dimensional data. I explained this how patterns which was difficult in our high dimensional data, because if we have a two directional data like plant height and biological yield. So this is our data of plant height and biological yield. And we shows that if plant height is increased, then biological yield was also increased. So this is the trend of plant height and biological yield. But if we include one another variable, this is plant height, this is biological yield, then here, this is the number of branches. So in bivariate data, we have easy to visualize our data pattern in bivariate data. But here, if we have data look like this, so we cannot easily interpret our data based on this visualization graph. So this is the most complex or most challenges in a multivariate data. So this is the patterns can be difficult to identify in high dimensional data. Why I say that? Where graphical representation becomes the challenging, because we have a 3-dimensional, 4-dimensional, because in our agriculture more than 3, it means like 10, 12, 13, 15, more than 30 also character was which was observed in our agriculture. So it may be very difficult to analyze or visualize our data based on graphical techniques. Therefore, PCA provides a powerful tool for exploring and analyzing complex data set. How? We see in next slide is another major advantage of PCA is data compression. Why data compression? Because it transforms the, like if we have a 30 character, 30 traits of our data. So PCA transform in 3 to 4 PC, 3 to 4. It means 30D to only 3 or 4D. It means it is then 30D is very difficult to visualize and as compared to 3 or 4D data. So that's why PCA is data compression technique. It reduces the number of dimensions while retaining most of the important information contained in original data set. Because our original data is shows 30 traits, while in principle, after using principal component analysis, it is used only 3 to 4 PC or 3 to 4 dimensional. Thus, PCA helps in pattern recognition, dimensionality reduction, and visualization and simplification of multivariate data. Okay. Now, how it's performed or how principal component analysis do the dimensional reduction in our multivariate data. So, principal component analysis is a multivariate statistical technique. Why multivariate? Because it is used for 3 or more than 3 variable. 3 or more than 3 variable. That's why it is the multivariate statistical technique used to transform a set of possibly correlated variables. Because I explained this, if we have a x1, x2, x3 and up to xp, like here we have a 13 variables, 13 traits of our agricultural data. So this is all are correlated with each other. We know that if plant height is increased, then biological yield was also increased. Then plant height is increased, then our grain yield is decreased. Number of branches is increased, then biological yield is increased. Okay, so this way our all the variables are correlated with each other in smaller, more proportional. So here is principal component analysis transform a set of possibly correlated variables into a smaller number of uncorrelated variables, uncorrelated linear combination. Why it is linear combination? So we see in next slides. So here, this all the variables, we have a 13 variables of our agricultural data. So it transform in PC 13. So these all the 13 principal components are uncorrelated with each other. It means correlation between them, it is near about 0. It means this is non-significant result of correlation. So this way, principal component analysis transform the original correlated data into a uncorrelated linear combination, which was called principal component. Okay. Now, the principal components are new variables, not simply selected original variable. So here, this is our original variable, which was 13, and these are new variables. which was not equal to our original variable. These are transform value of our original variable. Then the important point is that PC1, PC2, like here I say example of only two principal component analysis, 2 PC. So these are the linear combination of our original variable. Why linear combination? See, like here we have a x1, x2, and x3. Here I see only 3 variable or 3 type. So PC1, it is the linear combination of these 3 variable. Okay. So PC1 is equal to A11 x1 plus A12 x2 plus A13 x3. So this is the linear combination of our variable. Okay. Here x1 is the value of our original variable x1, x2 is the original value of our x2, same x3. Here A11, it is the coefficient of x1. It means it shows the how much of variation which was explained by PC1 for x1 variable. It means if A11 found 0.7, it means 70% of variation, 70% of variation of x1 variable, x1 trait, variation of x1 trait which was explained by PC1. Okay. If A12, it means it is the coefficient for our x2 variable. If it's found 0.3, so here it means 30% of variation, 30% of variation of x2 variable or x2 trait which was explained by PC1. Remaining 70% for x2 variable which was explained by another principal component. Okay. Then same for PC2. So it is the linear combination of our independent variable or our variable. So this is the A21 x1 plus A22 x2, then A23 x3. Here I said 21. Here 21 means it is the coefficient for x1 for principal component 2. Here 1 means for first variable. Here 2 means it is the coefficient for second principal component for second variable. Okay. So this is that's why the principal component, it is the linear combination of our original variable. Okay. Anyone have a question? How it is the linear combination of our original variable? Okay. So PCA transforms our XP variable. Here XP means if we have a 13 variable. Okay. We have a 13 variable. So PCA transform in 13 PC. 13 PC, principal component. Here I say that these are correlated with each other and these are uncorrelated with each other. So PCA transform this original variable into 13 PC. So here some characteristic of PC is there. So like if our original data have a variance 100%. Okay. So this is the variance of original data. I explain in percentage so we can easily understand how it's performed. Original data. Okay. This is the variance for our original data set or original variable. It is 100%. So PC1 always explain maximum variance out of this 100% variation. It means if see for example like PC1 explain 80% of variation out of 100%. So remaining 20% of variation which was explained by another variable, another principal component like PC2 explain 15%. Okay, so here I say here I write that PC1 explain the maximum variance. I say that 80% of variation out of 100%. This is just for example. This is just for example. So here I say that out of 100% of variation, PC1 always explain maximum variation. Like just for example, it is 80%. Then out of remaining, so here remaining is 20%. So out of remaining variation, PC2 explain much maximum variance out of remaining. It means 15%. 15% of variation was explained by PC2. So here I write that PC2 explain maximum variance, maximum remaining variance. Here mention that word remaining variance. Here I not mention remaining variance because out of 100% this shows the maximum variance. It is 80%. So remaining is 20%. So out of remaining variance, PC2 shows the maximum variance. And same for PC3. So here remaining is only 5%. Okay, because 80% was explained by PC1, then 15% was explained by PC2. Now remaining is only 5%. Okay, so out of 5%, PC3 explained maximum remaining variance. It is 3%. Then now it is 2% is remaining. Then PC4 explained 1.5 remaining variance. Okay, so same for all the principal component analysis. So here I explain PC1 explain the maximum variance out of total variance. Out of total variance. It is 100%. Okay. Out of 100%. Now PC2 explain the maximum remaining variance. I say that if PC1 explains 70% variance, then out of remaining it is 30%. So out of 30, PC2 explain the maximum remaining variance. It is like 25%. Okay. Now remaining is only 5%. So subsequent PCs explain progressively smaller amount of variance. Why smaller amount? Like because PC1 explain 70%, 70%, then PC2 explain 25, then PC3 it is 3%. So here we shows the trend of our explained variance is decreasing rate. Like first is 70%, then 25%, then 3%, then 1.5, and so on, 0.3, 0.2, 0.1, and so on. Okay. So that's why subsequent PCs explain progressively smaller amount of variance. So for exam purpose, I says that PC1 always shows the maximum variance out of total variance. Okay. Here PC1 shows or explain. Here explain is better word. Explain maximum variance out of total variance, followed by PC2, PC3, and so on. Okay, so most in some exam, this question was repeatedly asked. Like PC1 shows the shows or explain, here shows not, explain maximum variance out of total variance, followed by PC2 and PC3 and so on. Okay, so here all the PCs are uncorrelated or mutually uncorrelated with each other. It means they are orthogonal to each other. Okay, for variance purpose, if anyone have a question.
Why PC1 show maximum variation?
Okay. Like if we have a data like this, okay, like here we take only two-dimensional data, y and x. We have a data is look like this. So this is our trend of our data. Okay. So first, we rotate our data in such a way, that like this is a PC1. Okay. So PC1 always perform in that direction which shows the maximum variance. So this is our trend of our data is this, then this is the PC1. We consider it as a PC1. Then second then PC2 is drawn. Here I draw that this is PC2. Why I draw in this direction? Because here we have a 90% of an angle. Here we have a 90% of angle because PC1 and PC2 are uncorrelated with each other. Okay, so that's why I draw PC2 in 90 degree of angle of PC1. So PC1 is draw in a trend line, or we say that explained variation direction. So this is the explained variance direction of our data. Okay, that's why PC1 has the maximum variance out of all the PCs. Okay.
Okay, sir. Okay. Okay.
Now, imagine a cloud of points in 2 dimensions. The data may have a long direction and short direction. I explain with this graph easily. Okay. So this is our original variable x2 and x1, which are positively correlated. Why positively correlated with each other? Because like here we see with one graph. This is y and this is x variable. Okay. So if x was increased, then y is also increased. Okay. So here this is x, this is y, this is x, this is y. Okay. So here x is increased, then y is also increased. So this is the graph for positive correlation. Got it? Then here second graph y and x. If here data look like this, if x is increased, here x is increased, then y is decreasing, right? Okay. So for this, here x is increasing, but y is decreased. So that's why it is the negative correlation. This is positive correlation. Okay. So this is the basic idea behind positive correlation and negative correlation. So this is our two variable x2 and x1. These both variable have a data look like this. So this is, we saw that this is the positively correlated with each other. And this is the trend line of our x2 variable and x1 variable. Okay. Which shows the, this line shows the pattern of our data between x2 variable and x1 variable. This is the graph for our original variable. Okay. This is the graph for original variable which are correlated. This is correlated. Why? Because it is the positive correlation between x2 and x1. Now, principal component analysis is, it is the rotation of axis, like how it is rotated the data. So here now x1 is rotated in look like this, which direction? So this is our data line or trend line. This is our data line, which is PC1. Now it is PC1, or you can say x-axis. Okay. So here we know that x-axis and y-axis are always at 90 degree of angle. 90 degree of angle, because these two axes are orthogonal to each other, or which are not correlated with each other. This is only for example why it is 90 degree of angle, because these two are orthogonal to each other. So here now this is our data pattern. It is called as data pattern. Now it is PC1. Now it is PC1. PC1 direction is always at the direction of maximum variance. Here I say mention that direction of PC1 is always a maximum variance. So here our variance between two variables it shows like this direction. Okay. So this is PC1. Now it is considered as horizontal axis or x-axis. Okay. Now PC2, we have to perform PC2 in such a way that that y-axis or PC2 axis are orthogonal to PC1. So this is the PC2. This is the PC2, and this is the angle between PC1 and PC2 in such a way that this is the angle between PC1 and PC2. It is 90 degree. 90 degree, it means this both PC1 and PC2 are orthogonal to each other. Orthogonal to each other. Okay, so we have to rotate our data in a such a way that the PC1 and PC2 are orthogonal or uncorrelated with each other. So we have to perform our perform after PCA. We have to PC1 and PC2. These are two new axes of our data, original data. Our original data is X1 and X2. This is our original data. And PC1 and PC2, it is the new axis of our data, which are uncorrelated with each other. Here X1 and X2 is original axis or original data, which are correlated with each other, because here we see that this is the positive correlation between them. Now, this axis shows the PC1 and PC2. Both are uncorrelated with each other. So orthogonal, here I mentioned orthogonal means the principal components are perpendicular to each other. It means 90 degree to each other. Here I mentioned the angle between PC1 and PC2, it is 90 degree. So they are uncorrelated or independent to each other. Now here X1 and X2, it is correlated with each other because the data pattern is look like this. Here new axis, it is the pattern of our data. Okay, so this is the PC1. Now we have second direction, it is 90 degree of angle of PC1. Then this is the PC2. That's why it is the uncorrelated with each other. That's why orthogonal PC1 and PC2 are orthogonal with each other. Now,
if they are correlated, then their angle changes. Any change in angle?
Sorry?
If they are correlated,
okay,
there is change in angle, any angle?
Okay. So here you can see that if this line is weak origin, okay, we touch this line in origin. So here we shows that this angle is less than 90 degree. It is less than 90 degree or not?
Yes, yes.
Okay. So if the angle between two axes is less than 90 degree, then it is considered as a positive correlation.
Okay.
Now, if our data line is look like this, okay, this is negative correlation data. Okay, this is the data and this is the line of our data. So if we touch this line to x-axis, then this is the angle between two lines. It is greater than 90 degree. Sorry, greater than 90 degree. Then it is the negative correlation between them.
Okay. Thank you.
This was also helpful for in biplot analysis for our principal component analysis. We see in next slides for interpretation. Now, each principal component is a linear combination of original variable. I explained in our previous slides how it is a linear combination of original variable. So here we have two principal components. PC1, just for example, I mentioned here only two principal components. So PC1 is equal to A11 x1, A12 x2 up to A1p xp, because we have a p variable. Same for PC2. So this is the linear combination of our original variable. And here, this is the coefficient of our variable, which is our study. So Aij, it is the coefficient of variable for our principal component. So here, like we see that principal component 1, it is the 0.40x1, 0.35x2, 0.60x3, 0.58x4. It means 40% of variation, 40% of variation for x1 variable, which was explained by PC1. Okay. Remaining 60%, which was explained by another PCs like PC2, PC3, PC4. Same for x2 variable. Out of 100% of variation for x2 variable, 35% of variation was which was explained by PC1. Remaining 65, which was explained by another PCs. Same for x3, it is 60% of variation which was explained by PC1. Same for x4, it is 58%. Remaining 42% was explained by another PCs. So here, this is the contribution. So here I mention here, this is the 40%, 35%, 60%, and 58%. So this is the contribution. This is the contribution of variable or trait for generating PC1. Okay. So based on this coefficient, can anyone tell which variable has the highest contribution for generating PC1? Anyone? Based on this coefficient, can anyone tell me?
First variable, x3.
No.
Third
0.6.
variable.
Yes, third variable has the highest contribution for explaining much variation. It means here only 40% of variation was explained, here 35, and here 58%. But for x3 variable, it is 60% of variance which was explained by PC1. Okay, it means here we generate PC1 based on our 4 character, So PC1 explain more variation for x3 variable is followed by x4 and x1 and x2. It means x3 variable are responsible for generating PC1 or generating new axis of our data. So this coefficient shows the contribution of explaining variance out of 100 for PC1. Okay, now you understand what is the coefficient for our independent, our trait for PC1. Got it, all the participants? Okay. So this means PC1 is influenced by all 4 traits, but the magnitude of their coefficient is different. So this helps us to understand the importance and direction of variables in the component. Okay. So this is this coefficient is important to understand the which direction or which way we have to explain our variance by our PC1. This shows the magnitude and direction of our explained variance. So based on this coefficient, we can say that x3 is more responsible for developing new axis. It is called PC1, and PC1 was always explain maximum variance as compared to other principal component. Now, how we generate PC1? PCA analysis. How we perform this based on our mathematical formula or such a way. So, like this is our matrix of our data, because in multivariate data, always we deal with matrix form. Here, matrix form. In multivariate data, we always deal with matrix. Okay. So matrix, it is the combination of row and column. It is the combination of row and column. So this is the row of our matrix x1, x2, 1, 2, 3, 4 up to n. Okay. So here n row is considered as a number of genotype. If we have a 10 genotypes, so 1, 2, 3, 4, 5 up to 10. So this is the row of our matrix. Okay. This is the row of our matrix. And if we study with three variables, x1, x2, and x3. Okay. So this is the column of our matrix. Column of our matrix. So here we have a 1, 2, and 3 column because we have a 3 variable at a time. x1, x2, and x3. Okay. So this is the column of our data. It is known as variable, and row of the data or row of the matrix is known as the genotype or response or observation. Like if you have a survey data of 10 farmer, so 10 farmer, it is 10 farmer is always row. And if you study with education and facility of education and so on. Okay, so this is the variable of our study. So this way, if you have a 4 variable, then column is 4 and 10 farmers, so 10 is row. So this way we generate row column matrix for our data, multivariate data. So we have a p variable. So here we have a p column, 1, 2, 3 up to p column. Here we have a n observation. N observation means if we have a n genotype. So here we have a n row, 1, 2, 3 up to n. Okay. So we have a n by p matrix. N by p matrix. So here always matrix is denoted as n by p. Here n is row and p is column. Okay. This is just for a example or just for your exam. So this is row and column. If we have a 3 row and 3 column, so this is denoted as a 3 by 3, or this is also known as square matrix. If you have a 10 genotype, so this is 10, it is row. If you have a 4 variable, so this is 4 column. So it is the 10 by 4 matrix. Okay, so this is the type of our matrix, 10 by 4, 3 by 4, or n. Generally, it is denoted as a n by p. N it is row and p it is column. Now, here I explain one more thing. Like if we have a data x1, x2, x3. x1 it is plant height. x2 it is our days to 50% flowering. And x3 it is yield. So here plant height is measured in centimeter. Days to 50% flowering, it is measured in always count, like okay, count. We said that count. Then yield is measured in kilogram. Okay, so all the variable have a different unit. Like first one have a centimeter, second one have a count. It is a no unit, but it is count. Like then third unit, it is your yield. It was measured in kilogram. Okay, so x1, like if plant height is found 100 centimeter, 150 centimeter, 180 centimeter. Okay, and then x2 variable, it is measured that days to 50% flowering, like 40, 42, 43. Then x3 variable, it is yield. So yield is look like a 2 kilogram, 3 kilogram, or 4 kilogram. So all the variables are measured in different unit. So here, based on this data, we can see that x1 variable have a higher magnitude of data because it is measured in centimeter as compared to x2 and x3 variable. Here x3 variable is measured in kilograms, so that's why it has a value of 2, 3, or 4. So it have a lower magnitude. Okay, lower magnitude. So this is the biasness for our variable, because x1 variable get the higher magnitude for the data because this is measured in centimeter, followed by x2 and x3. And x3 variable have a lower magnitude based because this variable is measured in kilogram. So first we have to standardize our data in such a way that all the variables are transformed in single scale. Single scale. You got it? Why I say that we have to transform our data in a single scale? Otherwise, I'll repeat again. Hello, Arvind? You got it?
Yes, sir.
How we standardize our data?
Yes, 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 sir.
Okay. So this is the basic need for standardize our data because all the variables are measured in different unit. Okay, so this is the techniques for standardization of our data or standardization of our variables. So this is the also known as Z score or standard normal distribution. Why it is standard normal? I explained this. Standard normal. In your study, you can see that you can read that our data follow normal distribution with mean mu and variance sigma square. Okay, so here it means n means it is our data follow normal distribution. Okay, here mu means your variable have a like 30 gram of mean yield. It is the mean of your variable. Like if you have a variable x, it is yield. Okay, yield. So mean of the yield is 30 gram and variance of your data it is 3. This is the variance of your data, variance of a variable yield. So this is the normal distribution, and this is the denotation of our normal distribution, which is mean mu and variance sigma square. So here all the variables we have like x1, x2, and x3. All the variables are measured in different units. So obviously all the variables have a mu is different. So first one variable for planted it is mu1, it is mu2, and mu3. And all the variables have a variance is also different, sigma 1 square, sigma 2 square, and sigma 3 square. So first we have to standardize our data in such a way that all the variables have a mu is equal to 0. And sigma 1 square, sigma 2 square, sigma 3 square is equal to 1. So we have to standardize or we have to transform our variable in such a way that all the variable have a mu is 0 and variance is equal to 1. Okay, so if your data have a mean is 0 and variance is 1, it means it follows standard normal distribution with mean 0 and variance 1. Okay, so here we transform our normal distribution into standard normal distribution in such a way that all the variables have a mean 0 and variance 1. So how it perform? So here it is the equation. Here it is the equation for transforming our all the variable in such a way that all the variable have a mean 0 and variance 1. Okay, standardize our data in such a way. So here xij means if like our data is x1 variable have a data is 1, 2, and 3. So mean of the data is 2. X1 bar it is 2. Okay, because how it calculate 1 plus 2 plus 3 divided by 3. So 6 divided by 3 it is 2. Okay, so this is our mean of our data. So first we have to subtract all the value of our variable by their mean. So we have to subtract them -2, -2, and -2. Then we have to divide by variance of that data. Like variance is also 1, 2. Okay, so then 1 minus 2 it is -1, 2 minus 2 it is 0, 3 minus 2 it is 1. So first then we have to divide by variance of data. It is 2. So like it is a -0.5, it is 0, and it is a 0.5. Okay, so here now this is the new variable or new standardize our data. This is the standardize our data by using this formula. First we have to divide each observation by their mean, then we have to subtract, we have to divide by their own original value of standard deviation or variance. If square root of the variance, it is also called as standard deviation. So this is the original formula for how to standardize our data. So first we have to subtract all the observation of our variable by their own mean divided by standard deviation of the original variable. So this way we standardize our data in such a way that all the variables have a mean is equal to 0 and standard deviation is equal to 1 or variance is also equal to 1. Okay, got it? How we standardize our data and why we standardize our data? Can anyone respond? Okay. So after standardizing our data, all the variables are in a single scale because all the variables have a zero mean and variance is 1. Before we standardize our data, all the variables have a not equal mean. If mu1 is not equal to mu2 is not equal to mu3, because all the variables are measured in different unit. Because first variable is measured in centimeter, second is count, and third one is kilogram. So then we have standardized our data in such a way that all the variables are in single scale. Not I mentioned single unit, here I mentioned single scale with mean 0 and standard deviation or variance equal to 1. All the variable have a mean 0 and standard deviation or variance is equal to 1. Okay. So if PCA is based directly on covariance matrix, okay, like if you are not able to standardize your data, so here we have to use PCA by variance covariance matrix. Variance covariance matrix. Otherwise, correlation matrix is also there. Here, this is for example, or exam purpose. If you not standardize your data, then you have to perform PCA by variance covariance matrix. Variance covariance matrix. If you standardize your data, if yes, we have to standardize our data, then we use correlation matrix. It is also known as variance covariance matrix, but also known as correlation matrix. Why? Because if we have a like x1, x2, and x3, x1, x2, and x3. Here we know that diagonal element shows the variance of our original variable. So here, after standardizing our data, variance is 1. Okay, variance is 1. So here diagonal element shows that variance of original variable, it is 1. Okay, and also if correlation between x1 and x1, it is also 1. Okay, so that's why diagonal elements of correlation matrix, after standardizing our data, it shows the correlation between x1 and x1, it is 1, x2 and x2, it is 1, x3 and x3, it is 1. Then upper diagonal and lower diagonal elements shows the covariance matrix. Okay, so covariance matrix, like R is equal to, I explained in previous slide, it is the equation for correlation x1, x2 divided, equation for correlation, it is covariance for x1 and x2 divided by standard deviation of x1 and standard deviation of x2. But after standardizing, this is the standard deviation of x1 and x2, it is equal to 1. So here R is equal to covariance of x1 and x2. Okay, so in correlation matrix, diagonal element is shows 1, 1, 1, and upper diagonal element shows the correlation between x1 and x2. So it is covariance of x1, x2, then x1, x3. It is correlation so between x1 and x3, and also covariance between x1 and x3. That's why after standardizing our data, variance covariance matrix is also known as correlation matrix. This is after only standardizing our data, not before standardize. This is after standardize. Before standardize, it is known as variance covariance matrix. After standardizing, it is known as correlation matrix. Okay. Now, standardization put variables on a common scale or single scale, because all the variable have a mean 0 and variance 1. So this is the notation of how to notate our standardized data So here X follow standard normal distribution with mean 0 and variance 1. Okay. Now, covariance and correlation matrix. I explained in these slides why it is covariance and correlation matrix. So covariance matrix used when variables are measured on comparable scale. It means original variable. It means if we compared or measured our data in original scale, then it is known as variance covariance matrix. After standardizing our data, it is known as correlation matrix. It is known as correlation matrix. So this is the covariance matrix contain variance on the diagonal limits. Here we have a two variable, x1 and x2, then x1 and x2. So this is our diagonal element. This is our diagonal element. These two are our diagonal element. So this shows the variance of x1, variance of x1. And this element shows the variance of x2 because we have a two variable. If we have a three variable, okay, x1, x2, x3, x1, x2, and x3. So this element of matrix, also known as diagonal elements, shows the variance of x1, variance of x2, and variance of x3. Okay, so that's why variance on the diagonal element. Then covariance matrix variable of the diagonal. This is the upper diagonal and lower diagonal matrix are always equal because covariance between x1 and x2 and covariance between x2 and x1 is always equal. Covariance between x1 and x2 is always equal. Covariance between x2 and x1. Okay. So this element shows the covariance between x1 and x2. This element shows the covariance between x1 and x3. Same, this element shows the covariance between x2 and x3. Okay. So this is the variance covariance matrix. Then same for correlation matrix I explained in previous slides. So this elements, diagonal element shows the correlation between x1 and x1. It is always 1, 1 and 1. So here in correlation matrix, diagonal element is always 1 because correlation between x1 and an x1 for itself, it's always a 1. Okay. Then diagonal element shows the covariance between x1 and x2, but after standardizing our data, correlation is always equal covariance between x1 and x2. Okay, I explain in the again why standardizing after standardizing covariance between x1 and x2, it is always equal to correlation between them. Covariance between x1 and x2 divided by standard deviation of x1, standard deviation of x2. But I mentioned that standard deviation of x1 and x2 after standardizing our data, it is 1. Okay, so here R12 is equal to covariance between x1 and x2. So that's why after standardizing our data, variance covariance matrix is also known as correlation matrix. So PCA can decompose this matrix to identify the measured direction of variation based on variance covariance matrix. How we see that? So now we move ahead. So here, this is the equation for Fisher's criteria. So here S is denoted as a variance covariance matrix. Variance covariance matrix, or also known as correlation matrix if we standardize our data. Okay, so here it is the variance covariance matrix or correlation matrix. Here lambda, it is the eigenvalue. Here I, it is the identity matrix. Why it is identity matrix? Here, if we have a 3 variable, so we have to generate 3 by 3 identity matrix. 3 by 3. It means if we have a if we have a 3 variable p, p is equal to 3. So we have to generate our identity matrix in a 3 by 3. Here it is the square matrix of our matrix. It is the form of the square matrix. So here identity matrix, it is known as a diagonal element of the all the diagonal element of the matrix is equal to 1. Here diagonal element of our matrix is equal to 1 and off diagonal element is equal to 0. Okay, so this is the identity matrix. Here this is the identity matrix because our all the elements of our diagonal elements is equal to 1 and of the diagonal element is equal to 0. So here in this equation we know the variance covariance matrix, we know the identity matrix. So here we have to equate this equation. Here we have to equate this equation by 0. Okay. So here S is equal to variance covariance matrix. It is always known. Here identity matrix, I explained diagonal element is equal to 1. So here it is also known. So we have to equate this equation by 0 and we get the value of lambda. Here lambda it is eigenvalue. Here it is a eigenvalue. And this is the equation. It is known as a Fisher's criterion. This is very difficult in mathematical form, but I explain in easy way in basic way. So we have to equate this equation by 0 and we get the matrix of lambda. Okay. Here I explain what is eigenvalue and what is eigenvector. If we consider only single value of eigenvalue, it is eigenvalue, it is a single value. Okay, is the single value. So here eigenvalue tells how much of information or variability is captured by each principal component. Okay, like if eigenvalue found for PC1 is equal to 1.6, PC2 it is 0.8, PC3 eigenvalue found 0.3. So based on this eigenvalue, we can see that PC1 has the highest value of eigenvalue. PC1 has the highest value for eigenvalue, followed by PC2 and PC3. So based on this eigenvalue, we can say that PC1 has the explained maximum variance out of all the three variables. So eigenvalue tells that how much information or variability is captured by each principal component. Larger eigenvalue means that the corresponding principal component explain more variation in the data. So, okay, so based on this eigenvalue, we also conclude that which principal component explain more variation as compared to other variable. Then eigenvector. So eigenvector explain the direction of our PC1. Direction of our principal component. Okay, so eigenvector in PCA represent the direction or orientation of principal component in the multidimensional space. Okay, this is used in biplot analysis, in which eigenvectors which was useful for finding the direction of a principal component. Like if based on eigenvector we see that PC1 is in that direction, PC2 is in that direction, PC3 is in three-dimensional data, if PC3 is found in that direction. So which directions we have to generate axis for principal component, which was based on eigenvector. Okay. So eigenvector which was used for finding the direction of our principal component. Okay. Now variance explained by principal components. So if eigenvalues are lambda 1, lambda 2, and lambda p. So this is the lambda p. Here it is the eigenvalue for p pieces. Okay. Here we have a, like if we have a 4 variable, then principal component analysis performed 4 pieces. PC1, PC2, and PC3, and PC4. And here lambda 1, lambda 2, lambda 3, and lambda 4, which shows the eigenvalue which shows the principal component which shows the maximum variance, okay, based on eigenvalue, based on this eigenvalue. Now, after getting this lambda, we want to find how much of variation, how much of variance out of 100, which was explained by PC. So this is the equation for percentage of variance explained by PC. Okay, so how, like, example, here you have one example. Okay, here we have one example how to find the percentage explained variance based on eigenvalue. So here we have a 5 principal component: PC1, PC2, PC3, 4, and 5. This is the eigenvalue based on our Fisher's criterion equation. So based on eigenvalue, we can see that PC1 has the highest eigenvalue. It means PC1 shows explain the maximum variance out of 5 PCs. Okay. Now we want to find how much of variance which was explained by PC1. So here we have one equation: eigenvalue divided by number of PCs is equal to P. This is the eigenvalue into 100. Okay. So for PC1, eigenvalue for PC1, it is 4.20. Okay. It is 4.20 divided by number of PC, it is 5 into 100. So equate this equation. So we get 84%. It means out of 100% of variation of our data, PC1 explain 80% of 84% of variation out of 100%. Okay, remaining 16% of variation which was explained by PC2. PC2. Then if like 16% is remaining, so after 16 out of 60%, 40% of variation was which was explained by PC2. It was just example. Okay, so this way, based on eigenvalue, we can find the percentage of variance which was explained by PCJ. Here PCJ, it means which PC1, PC2, or PC3. Here we have a J principal component. Okay, so this is the equation for finding the percentage of variation explained by PC based on this equation or based on this eigenvalue. Up to this, anyone will have a question? So please put your question in chat box, or you can ask anytime. No, Gautam, we have no any facility for standardizing our data. But if you perform PCA analysis in AgriAnalyze, so it is automatically standardize your data and perform PCA analysis and give the better result for your data set. But we have no any independent tool for standardizing your data. Principal components are linear combination of original variable. I explained this, how this is the linear combination. Then principal components are mutually uncorrelated because this is PC1 and PC2 are orthogonal to each other. Same PC1, PC2, and PC3. All the principal components are orthogonal to each other. It means they are uncorrelated with each other. Then PC1 explain the maximum variance. Okay, I explained out of 100%, PC1 always shows the maximum variance. Then remaining variance, which was not explained by PC1, out of remaining variance, PC2 always explain maximum variance. Okay, so these 2 points are most important for your question, exam purpose and also for knowledge. Then successive components explain progressively smaller variance. It means explain variation PC1 always greater than PC2, always greater than PC3 up to PCT. Okay, this is the basic understanding for explained variance by PC. Then the total variance explained by all PCs are equal to the total variance in the original variables. It means if we sum all the PC explained variance by our PCs is always equal to, near equal to, not equal to, but near equal to, it is 100%. Okay. Now, PCA is sensitive to scaling and outlier. That's why we standardize our data, because if we measure our x1 variable in centimeter, x2 in kilogram, x3 in gram, then this is the biasness, or this is the magnitude difference between variables. So that's why PCA is sensitive to scaling. So we have to standardize our data. Okay, that's why we standardize our data. So this is the basic properties in PCA analysis. Now, like if we have a 13 variable, it means we have a P is equal to 13. So PCA perform, after PCA perform, it gives the 13 PCA, 13 PC, principal component. It means PC is equal to 13. So out of this 30, because this is the dimensional reduction technique, if we have if PCA gives a 13 principal components, so why we need this PC? We have to perform our analysis based on our original data set. But out of 30, we have to select how many PCs are most important or most explained variance. Okay, most explained variance or number of appropriate principal component. So based on these three methods, Kaiser criterion, script plot, and cumulative variance criteria. So based on these three methods, we have to decide how many number of principal components are used in our further study. So here I have one example. Suppose we start with 12 variables. PCA produce 12 PCs. We generally don't want to retain all 12 if our purpose is dimension reduction. Okay. So based on these three methods, we have to decide how many principal components are needed for our further study. So first, Kaiser criterion. So Kaiser criterion is a rule used to decide how many principal components should be retained in PCA. So when PCA is performed using a correlation matrix, it means standardizing our variable. The Kaiser criteria states that retain principal components having eigenvalue greater than 1. It means here we have a 5 principal component. Okay, PC1, PC2, PC3, PC4, and PC5. We have a P is equal to 5. And here we have an eigenvalue for each principal component based on Fisher's criterion equation. Okay, and here we show that principal component 1 have a 4.20, PC2 have a 2.15, PC3 have a 1.35, but PC4 and PC5 have a less than 1, 0.82 and 0.48. It means based on Kaiser's criterion, we have to select number of PCs in such a way that the which principal component have a less than 1 value or less than 1 value of eigenvalue which was rejected. Because PC4 and PC5 have a less than eigenvalue, it is 0.82 and 0.48. It is the less than 1. So we have to reject this principal component 4 and 5. Here PC1, PC2, and PC3 have a greater than eigenvalue, it is greater than 1. So we have to retain for our further study. Okay. So based on this eigenvalue, we have to decide the number of PCs based on this eigenvalue. Okay. Now another technique, it is a script plot. So in script plot, we have to plot our plot of number of principal component and eigenvalue. So in this technique, on x-axis, we have to plot the number of principal component PC1, PC2, and PC3, and on y-axis we have to put the eigenvalue. Then plot the eigenvalues in descending order and like this way. So this is the script plot of our data. Like we have a 12 PC. Okay, this is the 12 PC or component number, and this is the eigenvalue of eigenvalue. So here first PC has the highest value of eigenvalue. It is near about 4 point something. Okay, then PC2 has the 2, near about 2. It is 2. Then PC3 it has a near about 1 point something. Then PC4 has the less than 1. Okay, So here, based on script load, here we can see that here after 1 to 2, here we change the PC1 to PC2. So this is the drastically decreasing. Okay, here drastically decreasing the eigenvalue from 4.2 to direct 2. Okay, now if we move 2 to 3, so here 2 to 3 it is also drastically decreased. It means 2 to 1. Okay, but after 3 to 4, here we cannot significantly decreasing. Here it is 1 to only 0.8 something. Okay, so here we can also see that here elbow like structure is also shown. Elbow like structure is also shown. Okay, because here we see that drastically decreasing from 1 to 2, 2 to 3, but after 3 to 4, after point number 3 to 4, there is no any drastically decreasing because it decreased from 1 to only 0.8. So here, based on this script load, where this situation was happened or which where this elbow-like structure was seen, it means number of principal component which was desired for our study, it is 3. Okay, so at that point, our eigenvalue, the change decreasing rate of our eigenvalue, it is not significant. That's why we have to decide number of precision is equal to 3. At that point, we shows the elbow-like structure, and also in eigenvalue there is no any significant decreasing in eigenvalue. That's why we select the number of principal component. It is 3 based on this script note. Okay. Anyone have a question? Now, third method is look like here. Third method is cumulative variance. Cumulative variance criteria. It is nothing. I am not mentioning here, but it is nothing. Like if we found the eigenvalue for each principal component, and we found we calculate the variance explained by each principal component based on this eigenvalue. I explained 4.20. It is the eigenvalue for PC1 and divided by number of PC into 100. So it is 84. Same, we have to calculate the each for each principal component, and we get the explain variance for each principal component. From where which point explain variation like 84% for principal component 1, then 15%, sorry, 12% was explained variance by PC2, and then remaining 3 out of 3, it is a 2% of variation which was explained by PC3. After 2, it is 1% is remaining. Okay, so out of 1, PC4 explain 0.8, then PC4 explain 0.1, PC5 explain 0.1. Okay, now we have to cumulate this variance 84%. Then for second it is a 98%, because like here 84%, 12%, 2, 1. Okay, now 84% cumulative variance, then 98%, then here it means like 1. So here it is 99%, here it is 0.1, so it is 99.1%. Okay, so this way we cumulate the variance of our explained variance by our principal component. So at that point there is no any changes in our explained variance, because it is transformed only 99 to 99.1%. Okay, so here based on this cumulative variance we can find the number of pieces for our analysis. So here number of pieces is equal to 3 based on cumulative variance which was explained by PC principal component. Okay, so here some terminology which was used in our research purpose. So PC score and PC loading. So what is PC loading? So a PC loading is the coefficient or weight of an original variable in a principal component. So in previous, I mentioned that this is the coefficient which was used for which variable has the highest contributing to explain variance by PC1. So here I means 40% of variance which was explained by X1 in PC1, here 35%, here 60%, and here 58%. Okay, this is the coefficient of variable. Based on this variable, we can find that, we can say that, or we can conclude that which variable has the highest contributing character for direction of PC1. So this is the factor loading. Okay. Now, real example is that, like if we have a 4 variable: plant height, branch per plant, pots per plant, and granule per plant, and we find the PC loading 0.50, 0.45, 0.55, and 0.48. Okay, so here PC1 is equal to 0.5 x1 plus 0.45 x2 plus 0.55 x3 plus 0.48 x3. Okay, so this is the coefficient of variable in PC1. So based on this, we can find which variable are highest responsible for this PC1 formation. Okay, so based on this, we can conclude that pots per plant is the highest value of PC1 loading. It means 55% of variance, which was explained by PC1, followed by plant height, granule per plant, and branch per plant. Okay, so this is the PC loading for character. Here, pots per plant has the largest loading, 0.55. So it contributes strongly to PC1. Okay. Now, PC score. PC score is related with our observation or our genotype. The PC score is the value obtained for an individual genotype on a particular principal component. So here we have a 4 genotype, 1, 2, and 3, and 4. So based on this, we can find the PC1 score. So here we can see that if we plot by plot, here this is the by plot. This is our principal component 1, and this is principal component 2. Okay, so if we plot our genotype in this by plot, so this is the X value and this is the Y value. Okay, 2.35. So here it means it is a 2.35 is there. Then PC2 it is 0.42. So it means it is look like here. Okay, so this is the point for G1. So this way we can find the position of our genotype in biplot analysis of our principal component. This is the positional. This is the value of, this shows the position of genotype in a biplot analysis. Okay. So the PC1 score tells the position of our genotypes along the PC1 axis. So G1, it has the high positive position of PC1, and G4. So here G4, it has a minus 2.10. It means here it has a minus 2.10 and minus 0.30. So here it means here, that point, it is the minus 2.10 and minus 0.30. So this is the value for X and this is the value for Y plot. Okay, now you got it. How this is the PC score for tells the position of each genotype along the PC1 axis. Now, major uses of PCA. Before we go with uses, if anyone have a question, please tell me. Okay, Sunil Kole, in script plot, like here, I mentioned here that point. This is look like elbow-like structure.
Yes, sir.
Okay, this is look like elbow-like structure because after this there is a no drastically decreasing in eigenvalue. I mentioned here it is 1.01. It means here near about, for here it is 0.82. So there is no any significant difference between 1.01 and 0.82. Okay.
Okay.
So here number of PC is equal to 3 is basically required. So
Okay.
this is the basic idea behind the script note.
Okay.
Okay. Like here, I explain this again, PC score. Like here, this is the plot of X and Y. Simply X and Y. Okay. 1, 2, 3. 1, 2, and 3. So now I want to plot the A point in this graph at 2, 1. Then B point at 2, 2. Okay. So here, this is how we plot this A point in this graph. So here X value for A point is equal to 2. So here it is 2 and Y value for this A point is 1. Okay. So this is the point of A. Okay. You got it? How we point the A in this graph? Same for B. It is 2 and here it is 2. Sorry. Okay. So this way we point the A and B in this graph. So same way, this is the point of G1 in biplot. Here we have a positive and negative value. So here we have this type of graph. Here X and Y. This side of x-axis is positive. This side of x-axis it is negative. It is negative. It is positive. Same for y-axis. It is positive and it is negative. Okay. So here for G1 genotype, X value it is 2.35. So here X value it is positive. So it is 2.35 is here and 0.42. So 0.42 is look like here. So this is the position for genotype 1 in this graph. So PC score shows the position of genotype in our biplot analysis or in our axis graph. This is the value of x-axis and this is the value for y-axis. Here I mentioned x-axis and y-axis for better understanding, but in PCA we says the PC1 axis and PC2 axis. For better understanding, I mention here x-axis and y-axis. Okay. Now you got it? Yes. You can select the genotypes based on your biplot. Here I explain in interpretation part in next slide is how we select the genotype. So here we know the major uses of PCA. So first one is we know that dimensional reduction, handling multicollinearity. If in our data multicollinearity is there, so we have to perform PC analysis and we get the PCs which are uncorrelated with each other. Now these PC are used in our multiple regression analysis, and we get the prediction in we get the better prediction as compared to original data set. Okay. Now data visualization. If we have more than 3 variables, so visualization is very difficult. So based on principal component, we reduce the dimension of our graph. Then variable interpretation, then identification of important traits, then genotype selection, then multivariate data summarization. I explain in this in interpretation part. Okay. Up to this, anyone have a question? So please ask me. Otherwise, we move how to analyze PCA analysis by our AgriAnalyze tool. So our AgriAnalyze tool, all the participants are requested to register yourself in our AgriAnalyze tool. Okay. So how it is registered? So please follow my steps with your PC. You have to write AgriAnalyze in your Google. And here, first site which was shown is look like this. AgriAnalyze making statistical analysis coding free. In AgriAnalyze, there is no any coding which was required for your analysis. This is eco-friendly for all the member or all the researchers, which was not known coding in any software. So this is the site for our AgriAnalyze. So from this icon, you have to register yourself by filling this information, required information. If you are already registered, so you have to simply log in. After login in AgriAnalyze, here some tool was given like analytical tool, Excel tool, training, AgriAnalyze and pricing. So from any analytical tool, you have to go with here genetics and plant breeding section. So in that section, you get the dial analysis, genotypic correlation, phenotypic correlation, genotypic path analysis, phenotypic path analysis, cluster analysis by using Torcher's method, then principal component analysis, genetic parameter estimation. For stability here, Eberhardt and Russell model was given, then line by tester, then augmented RCBD. And if you are not a breeding student, if you are agronomical student, then here design of experiment in which CRD, RBD, Latin square design, split plot design, strip plot design, and also data transformation, which was also given. For social science student, here correlation and regression analysis tool is given. Multivariate analysis is given. PCA analysis also is there here in multivariate analysis. Then hypothesis testing was also given. So here we go with PCA. So in analytical tool, you have to go simply in genetics and plant breeding section. In this section, here principal component analysis which was given. Okay, so simply click on this icon, principal component analysis. I hope all the participants follow these steps. I repeat, in analytical tool, genetics and plant breeding, in genetics and plant breeding section, here principal component analysis which was given. Simply click on this icon. So here windows look like this. So here you have to upload your CSV file. Here you have to upload your data file in only CSV format. So click on choose file. I have also given dataset in your register PCA folder. Sorry. You have to upload CSV file of your data. Sample data is there. PCA sample data in your folder. You have to select this folder data file from folder and click on open. So here file successfully uploaded of our data. Then we have to select genotype row column. So this is the genotypes column. Here automatically trait was considered as a remaining columns which was considered as a trait. Okay. So first, before we go with this, we have to know we are data format. Okay. So we have a 9 characters or 9 traits of our genotypes. We have a 40 genotypes. Okay. We have a 40 genotypes with what, ma'am? Hello.
ये तो बारिश से कर रहे हैं
Okay. We have a 40 genotype with 3 replication. So we have a total 120 rows of our data set. Okay. So the first column is known as genotype. Then second is the DFF character. It is dash to 50% flowering. Then plant height. Then pod length. pod width, then harvest index, then test weight, then meal, then HRR and grain end. So this way we have a total 9 characters or 9 columns, and we have a 40 genotype with 3 replication. So this is the data structure of our data, sample data. Now, after choosing our CSV file of our data, then we have to click on genotype section. We have to click first column, which was considered as a genotypes. Other remaining are considered as a trait. Okay. Then click on submit button. So here, summary of your data set which was given. So we have a 40 genotype. Total observation is 120 because we have a 3 replication of our data set. Then traits, it is 9. So this is the Q amount of your research price. Here, total 23.60 rupees is there for PCA analysis, but currently it is free. So after getting this information for your data, simply click on submit button. Here it takes few seconds for analyzing your data set. So here, click on download button to get your analysis report. Here you get zip folder for your analysis report, because zip folder I have a image for your biplot analysis and also interpretation, a word file for interpretation. Then PCA output was also given in Excel file. So this way you get the output of your data, which have a 11 graph, 1 word file for interpretation, 1 Excel file for your output. Okay, so we see step by step which output was which tell. Okay, if anyone have a question regarding how to analyze, please ask me anytime. Anyone have a questions?
Hello, sir. Sir, can you repeat the steps again?
Okay. Okay, ma'am.
Thank you. So this is the AgriAnalyze site. Okay. So first we have to log in our site. After logging, here one icon is there, analytical tool. So in analytical tool, genetics and plant breeding section was given. In analytical tool, genetics and plant breeding section was given. So in that section, here, after cluster analysis, Stochas method, here one icon is there. It is principal component analysis. So simply click on principal component analysis in the section of genetics plant breeding and in analytical tool. So after clicking this, you have to get this window for principal component analysis. So we have to select your data file in CSV format. I explain what is the format for your data set in CSV file. So here we have a data file PCA sample data, which was given in zip folder. So this is the PCA sample data set in CSV format. So we have to upload this CSV file. So here you get the icon file successfully uploaded. Now in our data set, first column is for genotype listing, because we have a 40 genotype and 3 replications. So we have a total 120 rows, and in first column listing of genotype is there. So we have to select first column is the genotypes. Okay, so click on genotypes. You can get you can apply give name that you have based on your choice. Here we give genotypes for better understanding. So we have to select genotypes in this section. Here our site automatically detect the remaining traits. Remaining column is a trait. So we have a total 9 column for 9 traits. So remaining 9 columns, which was considered as a traits for our study. Then you have to simply click on submit button. So this is the summary of your data set with 40 genotype, total 120 observation. Here we have 9 traits. Okay, so currently we have this feature is free, and but if amount is there, so it is negligible, it is 23.60 rupees. So after getting your summary of your data set, if this is correct, then we have to just simply click on submit button. It takes few seconds for analysis of your data. So now here your analysis report is there. So we have to download your analysis report from this icon. Here you get the zip folder for analysis report, because in zip folder 11 graphs was given for your biplot analysis for PC1 and PC2. Here script plot for detail how to decide number of PC1 principal component. Here heat map was also given. Here we explain how we interpret this. And here word file, which was also given for interpretation of your principal component analysis. Then this is the output in Excel file also given. So this way you can get 11 images for your graph, one word file and one Excel file for your output. Now anyone have a question? Dr. Kuldeep Rajput, if you have a unreplicated data for your survey, okay, so then you have to simply click on analytical tool, then in multivariate analysis, here principal component analysis which was given for unreplicated data. Okay, so simply in this sections you have to click on to upload your data in such a way that first one is your individual, like if you have 10 farmers, so first one column give the name of first column, it is farmer, then list the 10 farmer. And if you have 10 variables or 10 traits, so simply put the 10 column and input the value of 10 variables in a 10 rows. Okay, so this is for unreplicated data. And in genetics and plant breeding section, it is for replicated data for genetics and plant breeding student. Okay, now this is the output for from your zip folder. So first one is the biplot of principal component 1 and principal component 2. So here vertical line shows the principal component 2 and horizontal line shows the principal component 1. Okay. Here this shows PC1 and this shows PC2. So this is the biplot for character and also genotype. So here, based on this direction of character in PC1 and PC2 graph, here we see that plant height and dash to 50% flowering in same direction. Okay. So these are correlated character. So this way we can find which variables are correlated with each other. So here we can find plant height and dash to 50% flowering are correlated with each other. And here, based on this graph here, genotype yielding and plant height, which was shows that there is a 90-degree of angle between direction of grain yield and plant height and dash to 50% flowering. It means correlation between genotype yield and plant height and dash to 50% flowering is non-significant. It means R is equal to 0. It means there is no correlation between grain yield and plant height and dash to 50% flowering. Okay, but for harvesting for grain yield and harvest index, it shows the less than 90 degree of angle. It means it shows the positive correlation between grain yield and harvest index. So based on this biplot analysis, we shows the direction, and correlation between variable. Okay, and also here for grain yield, here we see that for grain yield, G29 genotype has the highest value for grain yield. It means this genotype shows the higher grain yield for our from 40 genotype. Same directional relationship between grain yield and genotype 29. In here, genotype 18 based on PC1 and PC2, we can conclude that genotype 18 is most divergent or more divergent genotype as compared to other genotype. So based on this PC1 and PC2, we can find that genotype 18 is most divergent genotype among the all 40 genotype. And here we can also see that principal component 1 explain the 25%, 25.99, it means near about 26% of variation. Then PC2 explain 22.87% of variation. It means total variation was explained by PC1 and PC2 is near about 46%. It means remaining 40%, 54% of variation, which was explained by other PCs, PC3, PC4, or PC5, and so on. Okay. So based on this biplot graph, we can find the directional relationship between variables and which genotype was nearly about the which characters. It means genotype 29, which shows the most higher yielded genotype based on this biplot analysis. Genotype 2, it is near the principal component analysis. Here, if we have in AMI analysis, we have a 4 environment. Here we have a 4 environment. It means we have a variable, it is 4. Okay. And genotype it is 5. Here we get the point of genotype 1, genotype 2, genotype 3, genotype 4. Here this is mean and this is the PC1. This is the biplot of PC1 and mean. Okay. So which genotype was lie near the axis of this PC1, which was considered as a stable genotype. This is also used for PCA analysis for finding stable genotype. Okay, this is the most useful purpose of PCA in our agriculture. This is for finding stable genotype based on this biplot analysis of PCA, PC1, and mean yield. So here, based on this, we can find that genotype 1 it is stable, but this is lower yielded genotype because yield of this G1 is this genotype is stable but also high yielded genotype because mean of the G1 is greater than mean yield, because this is the greater than mean yield. So based on this biplot analysis, we can also find the stable genotype and high yielded genotype in AMI analysis, and also we can find the direction of characters based on this PC principal component analysis. This was also also shows the this is the mixed graph of genotype and variable. This is the independent graph of our variable. So based on this, we can find here that this is the orthogonal variables, grain yield and plant height and days to 50% flowering. And this is the positively correlated variable, plant height, days to 50% flowering with tiller weight, TW variables. Here also we found that this is the positively correlated variables. Here we found that harvest index and plant height was found negative correlation, because this here angle between harvest index and plant height, it is the greater than 90 degree. Greater than 90 degree angle was shown between harvest index and plant height. So this is the negative correlation between harvest index and plant heights. So this way we use this graph for finding directional relationship between two variables. Then this is the genotypes, genotype in byproduct analysis, position of genotype. So here we found that genotype 2 has the highest value of principal component 1. Okay, this is the PC1 score for G2 variable, but this genotype have a lower value for PC2. It means genotype 1 explained variance of genotype 2 is most by principal component 1. Okay, this is based on PC score, which was explained in previous slide. How we plot this genotype based on PC score. So this is the axis of X and Y. This is the position of genotype 2. This is the position of genotype 1 based on PC score. Okay, so this way we find the position of biplot analysis in the genotype, for position of genotype in biplot analysis based on PC score. Then this is the script plot which was given in your output folder. So here we plot the eigenvalue versus number of principal components. So here we have a 9 principal components because we have a 9 variable. And this is the eigenvalue. So first variable which was have the highest value of eigenvalue, it is 2.3, followed by principal component 2, it is 1.9, then it is 1.4, then 0.9, 0.8. But here we can see that this is the drastically decreasing the value of eigenvalue from 2.3 to 1.9. Then it is a 1.9 to 1.4, then 1.4 to 0.9. But after this point, there is no any drastically changes in eigenvalue. So here we have to select number of PC is equal to 4, which was appropriate for our PCA analysis. Okay, so based on this script plot, we can decide the number of PC in our PCA analysis. Okay, this is the same graph, but this is the percentage of explained variance. So here first principal component explained 26% of variation, followed by principal component 2, it was explained 20.9%. Then third variable which was explained 15.8, fourth variable it is 10.5, then fifth is 8.6, and so on. Here one also one rule is there, which variable has the explained variation is greater than 10, which was selected as a principal component. Others are excluded. So here this variable has the greater than 10 explained variation, so this was selected, but this variable, this principal component has the explained variation is less than 10, so it was rejected. So here we have to accept only this for principal component. Okay, so based on this we can also find the number of PC. Okay, now this is the example of see the example of AMI. Okay, we have a 40 genotype, and this is the principal component 1, and this is the mean. Okay, so if genotype 2 it is near to axis PC1 axis, so here basic rule is that this genotype is considered as a stable. It means with genotype which genotype was lie near to PC axis, which was considered as a stable. Okay. Here also it is G16. It was also stable, but G2 genotype has the greater value of mean yield as compared to here. This is the mean yield. Okay. This is the mean yield. So G2 has the positive mean yield. It means genotype 2, it is stable and also higher yielder. But genotype here, genotype 16, here this is the genotype 16. Here, genotype 16, it is stable but lower yielder. Okay. And here, if we have a 4 environment, so this is the position of environment 1. This is the position of environment 2. This is the position of environment 3. And this is the position for environment 4. So here we can also conclude that which genotype which was lying in point 11 environment 2, which was favorable in environment 2. Okay. So genotype 31, genotype 41, 14, 15, 39, 25, and 28, which was favorable only in E2 environment. Here E7, which have a higher yielder genotype, because this genotype have a higher yielder. So this genotype is known as a favorable genotype, because this environment has the higher PC value and also higher mean value. So this genotype is considered as a favorable genotype. Okay. So this way we can find the stable genotype and favorable genotype, and which genotype which was stable in which environment. Based on this in AMI model, we can find which genotype is stable and high yielder, which genotype was stable in which environment is also says by that this by-product analysis. Okay. Now you get Muhammad Kamran, you get it? Okay. Now, this is the heat map or correlation between, principal component and variable. So based on this, we can also find which variable was responsible for generating axis for principal component. So here we can find that days to 50% flowering, plant height, TW variable, it means test weight, which variable have a higher value of correlation. So which means we says that each variable are highly responsible for PC1. It means PC loading for this variable are higher in PC1 based on this heat map. In PC2, we can see that pod weight, grain yield, with these two characters are highly responsible for PC2, because this variable have a higher correlation. In PC3, pod length, meal, and HRR character are highly responsible for PC3. It means loading of these variables are higher in PC3. Same pod weight and grain yield was higher principal loading in PC2. Same days to 50% flowering, plant height, test weight was shown higher in PC1. Okay. So this way, based on this heat map, we can find which variables or which characters are highly responsible for developing or generating axis. Axis means PC. Based on this heat map or correlation. If anyone have a question regarding any point of PCA, then please ask me.
Hello, sir.
Yes, Dr. Kuldeep.
Yes, sir. First, you said that as per rule, if eigenvalue greater than 1, then we should select this for the PC purpose. And here
Yes,
the PC4 have eigenvalue less than 1, and you selected for the study purpose. Can you elaborate how and why? In skill
sir,
plot.
sometime it may be due to some. 1 minute. Okay. In our example, here we say that eigenvalue is 0.9, but explain variance which was greater than 10.5. So it may be based on some data. We have in that type of data we have to break some type of rule. Okay. So but it is less than 1, but it is near to 1. Okay. But explain variation which was greater than 10.5. Okay. If you take this only three component, if you take only three component in your data analysis, then it is also true. It was also true, but here you forgot 10% of variation. Here you forgot 10.5% of variation, which was significantly higher for PCA. Okay, so that's why in some data here we have to break some type of rule. Okay, here you take only three component in your analysis, but here you forgot 10.5% of variation in your data set. That's why we have to break this type of rule. Now you got it, Dr. Kuldeep?
Okay, sir.
Anyone who have a question? Welcome, Emul Sutar. I think no one have a questions regarding PCA analysis. We provide one link for feedback for today's session in our group. Please provide a valuable feedback for us. Yes, we will provide our recorded session in a short time in our group. So you can repeat or you can restudy of PC analysis by recording session. Okay. Thank you, dear all the participants, for attending this valuable session. And thank you, AgriAnalyze, for giving this opportunity to me. Okay. Thank you, all the participants.
Thank you, sir. Thank you.
Okay. Thank you, Imran.
Thank you, sir.